Module 5, Limits of the Theory, Welcome to Real Life. This module has been built on the progression from arithmetic through algebra, calculus, and differential equations presented in the previous modules. With that in mind, there are two main outcomes for this module. The first one is we are going to use a model of a biochemical reactor whose equations are going to be described in words as an alternative to reading its terms individually. And using these differential equations and the simulation, we will show how these kind of models can be used to reveal the existence of multiple possible steady states, for example. And the second one has to do with the fact that having a deterministic model does not guarantee either the existence of a solution or its use to predict the future behavior of the system. The biochemical reactors are used to produce intermediate and final products in several industries such as pharmaceutical, food, and beverages. These models are similar to other reactors as the same material balances are used. For this module, we are going to use a very simple one using only two components: the biomass, that are the cells that consumes the substrate. For example, in a fermentation, biomass are the cells that eat the sugar to produce alcohol. The biomass concentration is going to be represented by the state variable x sub 1. And the second state variable x sub 2 is the substrate or the sugar as mentioned in our fermentation example. The first equation models the dynamic behavior of the biomass concentration, namely the cells in the fermentation process. This is the differential equation, and we can see that the number of cells in the reactor can be either increased or decreased. They are increased by the rate of growth in the number of cells in the reactor and is decreased by the dilution rate of the cells in the reactor's mixture. These are the formal definitions of those variables. The second equation models the substrate dynamic concentration, namely the sugar in our fermentation process. This differential equation is much more complex than the previous one, but still we can read what the different terms are about. Concentration of the substrate in the reactor changes in time as the different components of the differential equation add or subtract to the concentration of the substrate. The substrate concentration will be increased with the addition of more substrate in the feed, and it can also be decreased by the growth of cells in the reactor. These are the formal definitions of those variables. The last equation that we need in order to complete our model is the growth rate, that is not constant, but it is a function of the substrate concentration. The expression looks like this, and it has to do with the two most common expressions used to model the growth rate. The first one is monod, and the second one is substrate inhibition, the latter being the one that we have chosen for our modeling in this module. Mu sub max is the maximum specific growth rate, K sub m is the saturation constant, K1 is the inverse of inhibition constant, and lastly, for those interested in further details on how are these equations derived and used, I suggest the reader to consult the Process Control Modeling, Design, and Simulation book written by Wayne Beckett. We have used those equations to build this Scilab XCOS simulator. The different variables are identified in the different places, and the simulation allows us to run different scenarios. The first one, we have as initial conditions for the growth rate and the biomass equals 1, we can see that the two concentrations get to a steady state, the biomass concentration being around 1.53 and the substrate around 0.15. In our second simulation and scenario, we see that if we start with x sub 1 equals 0.99 and x sub 2 equals 1.51, the two dynamic behaviors end up diverging. And the last one, we can see that the steady state reached by the substrate concentration and the biomass concentration are the same, except for a transient behavior observed at the beginning for the substrate concentration. The numbers used for that simulation are these ones. The second set of differential equations come from an unexpected source, chaos theory. Up until 19th century, and as per the classical physics, it was believed that given the initial state of conditions of any system, all its future states could be calculated. That was the clockwork universe that was holding true up until 1963, when Edward Lorenz from the MIT published his paper Deterministic Non-Periodic Flow, where he exposed that the notion of deterministic predictability, although appealing intuitive, is in practice false for most systems. And with this, it was made clear that determinism doesn't preclude chaos or unpredictability. And although it took 12 years for Lorenz's work to be noticed, it gave birth to what is known nowadays as chaos theory, which, by the way, has nothing to do with disorder. What Lorenz found from his simulation, he called it a strange attractor. His model of equations is a minimalist model of a thermal convection in a box. It's a simple weather model with a deceptive simplicity, but which has no closed form solution. His model revealed that the notion of deterministic predictability, although appealing intuitive, is in practice false for most systems. Lorenz gave with this birth to chaos theory. His paper, published in the Journal of Atmospheric Sciences in 1963, used three differential equations, x prime, y prime, and z prime. Prime meaning the derivative with respect to the dimensionless time. The constants sigma r and b are the Prandtl number, Rayleigh number, and a parameter b that is higher than 0. If we plot these three variables in the time domain, besides an oscillation that has to do with the normal movement of a convection system, there is no visible or pattern that is evident from here. But once we use a phase plane instead of a time domain based drawing, we can see that a pattern emerges. This pattern is known nowadays as the butterfly. And by the way, a phase plane means that instead of using the time to show the evolution in time of a variable, the different state variables are plotted against each other. And finally, for you to try and learn, this is the circuit that was created from the differential equations in the Lorenz paper. The values of sigma r and b are the same as he used in his paper. As a final takeaway from not only this module but from the entire course, we hope that this course has inspired your interest in dynamical systems, or that at least, if you didn't know it, that there will always be unintended consequences associated to any interventions that we as humans do on our surroundings and ecosystems of where we are part. Secondly, the modeling of biological and natural systems in general is more challenging, as its disaggregation has shown to remove traits that only emerge from a system as a whole. It doesn't necessarily mean that complex systems cannot be modeled by interconnecting simpler systems. And finally, as powerful as computers are in the study of the dynamical systems, we have to remember, as it has been postulated in the past, that when it comes to computers, garbage in, garbage out. Lest we forget. With this, we reach the end of our dynamical system for everyone who is interested. Short course. Thank you for tuning in. Until next time.